Now we are going to discuss a simple result in set theory, which is known as Demorgan's laws. Demorgan's laws talks about what happens if we take complement of intersection of two sets and union of two sets. Whenever we are talking about complement of a set, we have to be very clear about the universal set in which we are taking complements. For example, suppose that we are taking complement of the set of all rationals in the set of all rationals itself, we will be getting phi, the empty set. That is, let A equal to Q itself, and the universal set we are taking is again Q, then A complement is going to be empty set. But on the other hand, if U equal to the set of all real numbers, then A complement is going to be equal to the set of all irrationals. This is the difference that happens when we change the universal set. Therefore, whenever we are talking about taking complements, we have to be very clear about the universal set. So, for stating the De Morgan's laws, we are assuming that the universal set is the set of all real numbers, though it's not actually necessary. We can take it to be any set, but since we are in real analysis classes and we want to use this De Morgan's laws for proving various facts about real numbers, we will assume for our convenience that whatever set we are talking about will be a subset of real numbers. Now we are going to De Morgan's laws. So De Morgan's laws has two parts, and once we prove the first part, the second part is going to be more or less second part can be more or less proved in the same way. So we are making the statements first. The first statement is the following, and even before that we should make our assumptions. Let A be subset of R, they are subsets of real numbers. Then the first statement is the following: A intersection B complement equal to A complement union B complement. And the second statement is, in the first case we have taken intersection, now we take union. A union B complement equal to A complement intersection B complement. We will proceed to verify the first part. In the first part, we have to show that A intersection B complement equal to A complement union B complement. Whenever we have to show that two sets are identical, one usual technique is to establish that the first set is a subset of the second one, and the second set is a subset of the first. That means each of them are contained in each other. So we are going to follow exactly the same technique even here. We are assuming that we are going to take A intersection B, the whole complement, and we'll show that it's a subset of A complement union B complement. And on the other hand, we will show that A complement union B complement is going to be a subset of A intersection B. So we start from the LHS. Let X be an arbitrary element in A intersection B complement. We will finally show that this X belongs to A complement union B complement. Therefore, since X we have chosen is arbitrary, the usual mathematical way of saying that A intersection B, the whole complement, will be a subset of A complement union B complement. So we have chosen X from here. Therefore, X is in the complement means that X is not in A intersection B. That means that X is not in the intersection means that X is not in either A or X is not in B. X cannot be in both. That's the only thing. So X not in A or X not in B. Now, what is meant by X not in A? X not in A means that X belongs to A complement or X belongs to B complement. But this is or. Or means that we have to use the symbol union. Therefore, X belongs to A complement union B complement. So we have taken one element arbitrarily from A intersection B the whole complement, and we got that element to be there in A complement union B complement. Since X arbitrary, we have A intersection B complement subset of A complement union B complement. So the first part, LHS contained in RHS, is verified. Now we are moving to the second part. What is the second part? We have to take an element from A complement union B complement, and we have to show that that element belongs to A intersection B complement. So second part, we have to show that now we have to show that A complement union B complement is a subset of A intersection B complement. For this, as in the previous case, we choose an element from LHS. Let X be an arbitrary element from A complement union B complement. Therefore, by the definition of union, X belongs to A complement or X belongs to B complement. X belongs to A complement means that X is not in A or X is not in B. Now, X is not in A or X is not in B. That means that either X is not in A or X is not in B. But in that case, what we can clearly say that X cannot be there in the intersection, because if X has to be in the intersection, then X must be in A and X must be in B. But here what's happening? X is not in A or X is not in B. X is not in one of them. Therefore, X cannot be in A intersection B. Therefore, X must be in A intersection B complement. This is what we wanted here. Therefore, A complement union B complement. We started with an arbitrary element from A complement union B complement, and finally we arrived at the conclusion that that belongs to A intersection B complement. Therefore, A complement union B complement is a subset of A intersection B the whole complement. Previously, we have verified that A intersection B the whole complement is a subset of A complement union B complement. Therefore, clubbing these two arguments, we get finally that A intersection B complement is going to be A complement union B complement. Therefore, the first part of Demorgan's law is verified. Now, the second part is to show that A union B complement equal to A complement intersection B complement. For showing this, we have to exactly follow the same procedure. We have to show that left side is a subset of the right side and right side is a subset of the left side, so that both these sets will become equal. We are leaving this as an exercise. So part 2. Part 2 of Demorgan's laws is left as an exercise. Now we will see an exercise using Demorgan's laws. The question is the following. Let A1, A2, etc. An, they are all subsets of R. Prove that A1 union, A2 union, etc. union An, the complement of it is equal to A1 complement intersection A2 complement intersection etc. An complement. That means that union and complement will become complement and intersection. See, this is actually a general version, general statement of the property number 2 in Demorgan's law. In property number 2 of Demorgan's law, we have taken the union of two sets and we took the complement of the union of two sets. Instead of that, here we have to take the union of n sets. If n is equal to 2, this actually becomes the second part of Demorgan's laws. So we are going to assume the Demorgan's laws, and we are going to use Demorgan's laws and induction to verify this statement. So we are going to assume Demorgan's law, second part. By Demorgan's law, part 2, we have A1 union A2 whenever we have two sets, and complement, this is equal to A1 complement intersection A2 complement. Now, what is the assumption about induction? We have proved it for two sets, therefore the minimum number of sets we require is 2. Now, suppose that this statement is true for n minus 1 sets, we have to prove that this is true for n sets. We will use mathematical induction. Using mathematical induction, assume that the given statement is true for any n minus 1 sets, and we will prove that it is true for n sets. So true for any n minus 1 sets, therefore we can without any loss of generality, we can take the initial n minus 1 sets itself. So that is A1 union etc. union a n minus 1 complement equal to A1 complement intersection etc. intersection a n minus 1 complement. This is what is true according to our assumption, that the statement is true for n minus 1 sets. Now A1 union etc. union a n minus 1 union a, we take n sets. Now we take the complement, but this we can club as follows: A1 union etc. union a n minus 1 union a n and complement. Now we see this as a single set A. Therefore, for two, now we have only two sets A and AN, and for A and AN two sets, Demorgan's law is true. Therefore, this is equal to A1 union etc. union AN complement intersection AN minus 1 complement a n minus 1 complement intersection a n complement. Now the first part actually consists of n minus 1 sets, and by our assumption for any n minus 1 sets we have the union complement interchanges with complement intersection. Therefore we can write, we will just expand the first part: a1 complement intersection a2 complement intersection n minus 1 complement intersection an complement, but this is nothing but a1 complement intersection an complement. So we have verified the general version of second part of Demorgan's theorem, Demorgan's laws, and it would be interesting to see whether we can generalize the first part also. So what is the first part? A intersection B complement equal to A complement union B complement. The question is, try to verify A1 intersection B1 intersection etc. A1 intersection A2 intersection etc. AN complement is equal to A1 complement union A2 complement etc. union AN complement. This is an exercise for you. Now we will try to see the infinite version of the previous problem. So the infinite version means that previously we had taken A1, A2, etc. AN and the union and the complement. Instead of finishing or instead of stopping at AN, we will go up to infinity. So our next problem is the following. Is it true that union n equal to 1 to infinity an complement equal to intersection n equal to 1 to infinity an complement. So remember that in the previous case we have some I equal to 1 to n union ai and complement of that. Now in this case it's slightly different. So the very first thing probably we can think of is that this is going to be probably true. Okay, we will try without using any induction or anything like that. We will just try to verify it just by checking if the left hand side has an element, is it going to be there on the right hand side, and if the right hand side has an element, is it going to be there on the left hand side. So choose an element. Let x belongs to union n equal to 1 to infinity an complement. So what is the meaning of this? Therefore x is not in union n equal to 1 to infinity an. That means that x is not in the union means x is not in any of these elements. Therefore x is not in a1, x not in a2, etc. So x is not in a1, x is not in a2, etc. means that x is in a1 complement, x is in a2 complement, etc. Therefore if x is in all these sets, x must be there in the intersection also. Therefore x belongs to intersection n equal to 1 to infinity an complement. Therefore we have showed that the left hand side of the equality of these two sets, left hand side of this equality is a subset of the right hand side. Now to see the converse, the other side, choose x from the right side. Now let x is coming from intersection n equal to 1 to infinity an complement. Therefore x belongs to an complement for all n equal to 1, 2, 3, etc. Therefore x is in all an complement means that x is not in an for any n. That means x is not in a1, x is not in a2, etc. Therefore x is not in an means what? X is not in an for any n. So x is not in an for any n means that x is not in union n equal to 1 to infinity an, because if x has to be in union n equal to 1 to infinity an, x must be in at least one an, but that is not the case here. Therefore x is not in union n equal to 1 to infinity an. Therefore x is in union n equal to 1 to infinity an complement. So both these things put together, we have LHS subset of RHS and now RHS subset of LHS. Therefore these two sets are exactly the same. Here we didn't use induction. What is the reason for that? See, by induction what we proved previously is that any finitely many sets we choose a1, a2, etc. up to an, then we have the union of these sets complement is equal to intersection of the complements. But this is true, induction can be used only for proving that if there are n sets it's true, means if there are 10 sets it's correct, if there are 20 sets it's correct, if there are 30 sets it's correct. So the argument that we used previously is valid for any natural number. But here what is the number of sets? The number of sets is infinity. Infinity is not a natural number. Therefore we cannot say that by the previous induction argument the previous statement can be straight away generalized to infinite number of sets also. That is not true, because induction is true only for any finite number. What we are saying is whatever finite number of sets we choose, the statement is going to be true. In the case of infinite sets, induction is not at all guaranteeing anything. So this statement has to be proved directly without using induction. Now we will see another problem in using sets, but We will not be proving it using Demorgan's laws, but simple induction. Question is the following. Let A be a set with n elements. Then show that A has 2 raised to n distinct subsets. Here we can safely assume that n is going to be a natural number, or in fact if n is equal to 0, that means empty set, then also this will work, but that's not very interesting for us. We are going to use induction to verify this. As the first case, we will assume that A has one element. If A has one element and only one element in it, then its subsets are, suppose that A is equal to just A. What are the subsets of A? Subsets of A are this, and empty set is a subset of any set. Therefore, these two are the subsets. Therefore, how many subsets are there? 2 raised to 2 subset equal to 2 raised to 1. So, when A has just one element, the claim is true. Now we have to show that when A has n elements, then also it's going to be true. For the induction argument, we are assuming that whenever we have a set with n-1 elements, it's going to be true, and we will show that it's going to be true in the n element set case also. So assume that the given statement is true for any n-1 element set, and we will show that this is going to be true for any n element set also. Now we choose an n element set. Let B be an n element set. So we can write B equal to B1, B2, etc. Bn. Now B has n elements. We will form, by dropping just Bn, we will form another set. A is equal to, let A is equal to B1, etc. Bn-1. So this has n-1 elements. And how many subsets this A has? By our previous assumption, for any n-1 sets, our statement is true. Therefore, by induction assumption, A has 2 raised to n-1 distinct or different subsets. We have to show that B has n subsets. Now let S be a subset of A. So if S is a subset of A, definitely S cannot contain Bn. Now S actually generates a subset Bn. So S and S union Bn are completely different, because Bn is not there in S as Bn is not there in A. Therefore, corresponding to every S, we are getting another subset S union Bn. So how many? All this S is a subset of B, because B is a subset of A and A is a subset of B. S union Bn is also a subset of B. Therefore, corresponding to S, we are actually getting another subset. So for S, there are 2 raised to n-1 possibilities, and S union Bn, there are 2 raised to n-1 possibilities, and altogether we have 2 raised to 2 into 2 raised to n-1, that is 2 raised to n possibilities. So we have found, what we have now done is, so we have found 2 raised to n subsets of B. Now the question is that, have we found all the subsets of B? Because what we did now is take a subset of A. From that subset of A, we are generating a subset of B. But there can be some other subsets of B which are not of the form S union Bn, can that actually happen? Now, can we say that these 2n, 2 raised to n are the only subsets of B? So, otherwise, in other words, what we are asking is, whatever subset of B we are choosing, can you find an S that is a subset of A or that is a subset of A union Bn? So, let S1 be a subset of B. There are two possibilities. Case 1, Bn belongs to S1. If Bn belongs to S1, take S is equal to S minus Bn. So this S1 is actually coming from, therefore S goes to S union Bn equal to S1. Therefore S1 can be retrieved from a subset of A. Now, what is the second case? In the second case, Bn, suppose Bn not in S1. In this case, S1 is a subset of A itself. Therefore, S1 is actually a subset of A itself, and what we previously claimed is every subset of B must be a subset of A, or it must be a subset of A union An. That is true. In this first case, we are getting that that subset is a subset of A union Bn. In second case, we are getting that it is actually a subset of A. Therefore, every subset of B must be either coming from this side. Every subset of B must be either coming from this side or it must be coming from this side. That means that every subset of B belongs to one of these 2n minus 1 or 2n minus 1 class. Therefore, it belongs to this 2n subset. Therefore, we can have at most 2n subsets. We have, therefore, B has at most 2n subsets, but we have already found that B has indeed 2n subsets. So it has at most 2n subsets, it has 2n subsets. Therefore, clubbing these two statements, this and this together, we get B has 2n subsets. In fact, distinct subsets, verifying what we claimed. We used only mathematical induction in this case, and we proved that if it's true for the statement is true for n minus 1 sets, it's going to be true for n element set also. Therefore, by mathematical induction, the statement we made is true for any natural number n.